In mathematics and in computer science, we often look for things like patterns. And once we observe patterns, whether those be numerical or logical, we try to make some inferences about that. And so, we might observe that we start adding together two numbers and we find out that, it appears that every time I add two even integers together, I seem to get an output of an even integer as well. So when I do 2 plus 2, I get 4. Oh, look, 4 is even. 4 plus 2, well, that's 6, and that's an even number. If I do 2 plus 8, that's 10. That's also an even number. Well, an even number is any multiple of 2 or any number that you can divide by 2 and end up with another integer. So 10 is 5 times 2, 4 is 2 times 2, 6 is 3 times 2. And this doesn't stop at these numbers. 14 plus 12 is 26, and that's an even number. And so we might be tempted to say, oh, the sum of any two even numbers is always even. And that's where our logic and our intuition have a little bit of a disconnect, because it's inadequate to say, well, here's the pattern, look at the pattern, it must always hold true. We need to provide some sort of fabric without any holes in it that basically makes our logic foolproof and completely enclosed and sealed. So another claim, a person might have is that you can divide any two integers that you want. So for example, if you take 2 divided by 6, that gives you a real number. So the division of any two integers produces a real number. But then what if we forget about the situation where 0 is also an integer and you can't divide 3 by 0? So we've got to be very, very careful when we formulate our logic. Now in mathematics, a lot of statements are stated as implications. So there's some sort of condition. If the following conditions hold, then this result will happen. So in order to prove such a statement as being mathematically true, well, what does P implies Q mean? It means that whenever P happens, Q should also be true. So it suffices, in other words, for P to be true to guarantee that Q is true. And that is the only circumstance under which an if-then statement is true. The method of direct proof starts off assuming the premise, right? Because what we're trying to say here is if the premise is indeed true. So assume it is, and then show that the result Q follows. We often start off such a proof with suppose P is true. So we then have a series of logical steps that allow us to end with the conclusion. So there's suppose P is true, whatever that statement may be. Then you get to operate with that statement and do a bunch of logical steps, whether that is algebra or making some observations that are true. And then hopefully walking yourself to the conclusion Q. So it's as if I start over here on a path, right? And inch by inch, I sort of keep going and keep going and keep going and say, hey, look, I can always get to Q as long as P is true. And then eventually, once you get down here, you end up with the statement that you were trying to prove. And that's exactly what a direct proof is. So we get to use our propositional logic. We're not going to use truth tables. We've already used them to develop equivalencies. So sometimes when a direct proof is difficult, if you can't start at P and end at Q, there are some other techniques. So here's a real basic one. Here we have prove the proposition if x squared equals 9, then x equals plus or minus 3. You might say in your head, well, I already know that's true. But here we have the statement P. Here we have the statement Q. So the first thing we're going to do is, you usually say something like, here's the proof. So assume P is true, okay? So if P is true, that means assume x squared is equal to 9. So we basically assumed P. Okay, well now I want to somehow be able to conclude that x is plus or minus 3, but I just can't say, look, x is plus or minus 3. I've got to have some sequence of logical steps that allows me to arrive at what x must be. So when you assume x squared is equal to 9, well then it makes logical sense to say, oh, you know what, that's an algebraic equation. So if I take x squared equals 9, and I take the square root of both sides, and then I take the square root of, or plus or minus the square root of 9, then what I end up with is x is equal to, well, square root of 9 is 3, so x is equal to plus or minus 3. And we've just proven the statement. We've basically said therefore, and therefore you can write like this if you'd like. Therefore, whenever x squared is equal to 9, it follows that x equals plus or minus 3. And that is basically how you conduct a proof. Now this one's algebraic. Not all proofs in mathematics have to be algebraic. Some of them are very difficult and logical ones, but we're just trying to introduce how Boolean logic allows us to observe patterns and then make conclusions about them. So prove the proposition, if A and B are both even, then A plus B is also even. So here is what most students want to do, and me included when I was first studying this stuff. They want to say that, well, look, 2 plus 2 is equal to 4, 4 plus 6 is equal to 10. Oh, you want me to do some more? Okay, 10 plus 18 is equal to 28. I'll even give you a big one, 214 plus 106 is equal to 330, so that proves it all right there. But the problem is that only works when A and B are 2 and 2, when A and B are 4 and 6, when A and B are 10 and 18, and when A and B are 214 and 106. So if you only set off to prove it for those 4 pairs of numbers, you've succeeded. However, if you're trying to say that for any even integer A and for any even integer B, the sum of those numbers is also even, this is not going to suffice. So how do we do this? Well, first of all, we have to look at definitions. So what does it mean for a number to be even? Well, by definition of an even number, there is, and you always need to think about this, what is the definition of what I am talking about? What is the strict mathematical definition? So it's nice to say even, but you've got to give me a mathematical definition for it. So even numbers are the set, or E, capital E. This is not a required name of the set, but I'm just using capital E for even here. And the set of all even numbers is numbers of the form 2 times k, where k is some integer. So you can see, for example, if you write any even number, you could always write it as a product of a factor of 2 and something else. Every number is a multiple, every even number is a multiple of 2. So 2 is 2 times 1. And so you can think of k as being equal to 1 here. We can go on and on. We can say 22 is 2 times 11. In this case, k is this number right here. K is 11. So k is just any integer. And we want to remember that the set of integers, in case you've forgotten, is the set of all numbers 0, plus or minus 1, plus or minus 2, etc. So that's how we define even numbers. And so basically we should always be able to factor out a 2 from whatever number we're working with in order to be able to say it's even. So whenever we prove this, we're going to start off with the statement, suppose A and B are both even. And then we're going to say, well, that means A is equal to 2 times k1 for some integer k, k1. B is equal to 2 times some integer. And then we're going to take those two now mathematical quantities and combine them and show that their result is still even. Now the important thing to note here is k is just any integer. It doesn't really matter what integer k is, it just has to be the case that you can factor out a 2, and then whatever's left over as the other factor is your value of k. All right, that is, all even numbers can be factored into 2 and some other integer k. An odd number is, we'll also define that here because we'll work with those as well. The difference between an even and an odd is a plus or minus 1. Now, it could also be that an odd number is an even minus 1, but for simplicity, we'll just stick with the plus 1 convention. So if you double a number, for example, and then add 1 to it, it's going to be odd. In a similar sense, if I write 5, for instance, well, that's equal to 2 times 2 plus 1. So here is my value of k. If I write 11 as 2 times 5 plus 1, that gives me 11, and you can see that k is 5 in this case. 99 is equal to, let's see, if I subtract 1 from that, that's 98 divided by 2, so it's 2 times 49 plus 1, and again, k is just some integer, which is going to vary from odd number to odd number. So we don't really focus on the k, we just focus on whether it can be written as 2 times an integer, i.e. even, or 2 times an integer plus 1, i.e. odd. Okay, so now we're prepared, and along with one more fact that we'll need, this is called the closure property of integers under addition and multiplication. So we assume this to be true. It's difficult to prove, but if you add, it's often called an axiom. An axiom is just sort of an assumed truth because something becomes unprovable. If you sum or take the difference of any two integers, you always get another integer. And this is again not proof here, but if we take any two integers like 2 plus 11, we get 13, and that's still an integer. That's still a whole number. If you take -7 plus 36, you get 29, which is still an integer. You can take -2 minus 7, that's -9, that's still an integer, and so on. Same thing holds for multiplication. So if you multiply two integers, 2 times 3, you get another integer. -4 times -6 is +24, you get another integer. So these are assumed truths. Unfortunately, these are things that you cannot prove because there is no very strict definition for what an integer is. We just say an integer is 0 plus or minus 1 plus or minus 2. So we don't have a really operable definition. Okay, so let's go ahead and prove this statement now, that the sum of any two even integers is going to be an even integer. Now, we didn't say even integers, but when you see the word even, well, by definition, it's going to be an integer because it's the product of two integers, and by the closure property, an even number cannot be a fraction.